Hello and welcome to lesson 4.3 on complex numbers and simplifying radicals. So for context, where we're at in the unit is the last few videos we've been talking about quadratic functions, right? And that's the premise of this unit 4 is x squared, the quadratics, right? And what we're working towards in this unit is being able to use quadratics for real-world situations, apply them to a real context where we can solve problems, and use some of these algebraic techniques we've done to, apply to real things. But before we get to that, we've got to talk about something called complex numbers, which is part of what we study when we're looking at quadratics. And so that's what this lesson is. We're not really solving anything. We're not really doing a whole lot. We're just learning about maybe a new type of number. And that's the premise of the video. So there's a little introduction typed up here. And you could pause the video. You could read this, right, if you'd like. But here's maybe just a quick summary of what's all basically said right there. So I want you to go back to first grade. Pretend you are a 6-year-old in the United States with a typical first grader USA education. And you say, class, I would like to know what 5 minus 2 equals. And so you'd say, oh, teacher, 5 minus 2, I know how to do that. Well, 5 means that there's 5 things. There's 5 objects, like 5 apples, right? 5 coins, something like this, right? And if you say 5 minus 2, minus means to take away something. So if you had 5 objects and you had to take away 2, so that means I sort of cross out these 2, then I would count, I have 1, 2, 3 objects remaining. And so thus the solution to the equation 5 minus 2, or I guess the evaluation of the equation 5 minus 2 is 3. And you say, yeah, of course, right? And this is because if we start with this in first grade, but we also start with this historically, because how did we come up with numbers? Well, we wanted to quantify the stuff we interacted with, right? Physical, tangible objects. You said, let me quantify this so I can make comparisons, right? 5 is less than 20. And so I know, if I have 20 oranges, then I like that because that's better than having 5 oranges and I can split that up with my village or whatever, right? And I said, keep this idea and let's stay in first grade here. Let's reverse this. I said, class, what is 2 minus 5? And you say, 220. Well, 2 means I have 2 objects. I say 5 means to take away 5 of those. And I say, okay, 1, 2, what? I say, I can't do this, right? I say 2 minus 5, there's not 5 to take away from 2. 2 is less than 5. You can't do this. And so first grader says, this is not possible, right? And think about it. If you were asked this in first grade on a test, you probably said you can't take 5 away from 2. Right? And at that time in your math education, that was the answer, right? But eventually, you take more schooling, you learn more about numbers, and eventually we introduce this idea of a number line. And we say, actually, you could represent something called positive numbers and negative numbers, right? You could do something, or you say, this is 1, and that's -1, and -2, and -3, right? And you could say, so addition and subtraction could just be performed on a number line, where adding something means to go right on the number line, and subtracting something means to go left on the number line. And if you go below 0, then it's just the same number line, but backwards, right? And then we call those negatives. And so you say, then 2 minus 5 means to take 2, and to take away 5 from this means to go left 1, 2, 3, 4, 5. And so thus we have this result, -3, right? So at some time in your life, you said that this problem was not solvable. You said the answer did not exist. It was not possible. But then you expanded your concept of numbers and said, well, actually, there's this thing called negative numbers, and they play around just like positive numbers do. They interact the same way. They kind of follow the same multiplicative and additive properties, and they can represent physical things, even if you can't see it, even if it's not tangible, right? Tangible, meaning you can touch it, or you can feel it, you can see it, right? Even though you can't see a negative, you can conceptualize it, right? Because you could say, well, I'll say 2 oranges. I guess those are black. Let's call those bloranges. No, okay, that's yellow, so we'll call them yoranges. So I'll say, okay, I have 2 oranges here. And I say, take away 5. You say, okay, 1, 2. Ooh, there's not 5 to take away from. I say, well, then that means you owe me 3, right? And you say, oh, we could come up with this idea of debt. And so negatives could represent, okay, you had 2 apples, so I took away those, but you still owe me 3, and that's what's going to be represented by -3. And of course, this is really useful when we start dealing with cash, because then you could talk about money that's owed to someone, right? And so there's value in having negative numbers and using them for real life things. And I say, well, we're going to do the same thing today, something called complex numbers. And so the same way that you in first grade, you said, no, teacher, 2 minus 5 does not exist. Well, we're going to say the same thing and broaden our understanding, or deepen our understanding of numbers. And say, okay, so we're going to, I'll sort of show you this with 2 equations here. It says, for the 2 equations below, solve for x. So number 1, we got x squared minus 4 equals 0. And I would say, class, how do you solve this? And you say, well, you just need to get x squared alone. And so you'd say, I would add 4 to both sides, Mr. Spake. And I'd say, okay. Then x squared is 4. And then you'd say, okay, so what number squared, meaning what number times itself, is 4? And you say, well, even if you didn't know what that number is, you could take the square root of both sides like this. And they can say, oh, x is the square root of 4, means the number times itself that equals 4, and that answer is 2. And of course, something to keep in mind when you take square roots, right? Just a quick Algebra 1 reminder. Yes, 2 squared is 4. This is true. That's why when you take the square root of 4, you get 2. But also, -2 quantity squared, right, is also 4. So, if you're asking the question, what number squared is 4? Well, there's actually 2 answers. +2 is an answer, and -2 is an answer. And so we say, okay, ta-da, there it is. There's my answer. Because whether I take 2 or -2 and I square it, I get 4, and 4 minus 4 is 0. Done. So this has 2 solutions. Now I say, let's do it again, right? So I'm going to just slightly change this. And instead of x squared minus 4, we're going to change this to x squared plus 4. And I say, okay, class, do it again. And so you say, okay, well then x squared would be -4. And at this point, you take the square root of both sides. You say x is the square root of -4. And then, if you're thinking about it, right, and you're an Algebra 1 student who hasn't taken Algebra 2 yet, because you're taking Algebra 2 right now, and you haven't done a lot of independent research on this stuff, you'd probably say, hey, there's no solution here, right? You'd scream, hey, square root of -4? I say, this is ridiculous. You can't take the square root of -4. And you might ask, well, why not? I say, well, because if the answer is, if you're asking some number squared is -4, well, first of all, we already know the answer is 2 and -2. It gets you +4. So what in the world are you going to square to get -4? Because if you use a positive number and you square it, well, positive times a positive is a positive. And if you use a negative and you square it, negative times a negative is a positive. And even if you did 0, 0 squared would just be 0, which ain't negative, right? And that's what you want, is a -4. So then you'd say, okay, so then this isn't possible. There's no number that, when multiplied by itself, is -4. And so you'd say, okay then. The answer is no solution. And I say, you, my dear student, are doing 2 minus 5 and saying there's no solution. That's what you're doing right now. And I say, actually, there is an answer. There is something. Yeah? And the answer is square root of negative 4. Actually, that is the answer, right? You say, what? But you can't take the square root of negative 4. And I say, yeah. I guess. It's true that the numbers you're talking about, positives, negatives, 0, yeah, I agree. Positive numbers squared and negative squared and 0 squared, those aren't going to get you negative numbers. But those are something we call real numbers. And I say today we're going to introduce something called non-real numbers. Say, what is a non-real number? I say, well, a non-real number is simply not a real number. And a real number is this traditional concept of positives and negatives. So let's talk about it. How do we define this idea, right? What are you talking about? Non-real. Huh? What? I say, well, think about it. If something is not real, well, then it's fake. And if it's fake, that means it's made up. And if it's made up, then you've imagined it. So a non-real number we call imaginary. Yeah? So a non-real number is called an imaginary number. We're also going to use this word complex. Yeah? Now, they are a little different. They don't mean quite the same thing, but they're very related. And a lot of times people use these words interchangeably because when you're talking about complex numbers, you're talking about imaginary numbers. Yeah? And you're saying, what, Mr. Spake, you've already... Imaginary. And I say, hold on. Let me convince you. So first of all, we're going to make up this thing called a complex number, which is going to be written of this form. It says A plus BI. Okay? And we're going to talk about what this I means. But A is going to be a real number, so A will be called the real component. And this I basically stands for imaginary. So B times I is going to be called the imaginary component. And so what a complex number is, a complex number is a real number plus an imaginary number. Okay? And it's important to note that A and B are themselves real numbers. So what is this thing I? What the heck is that? And I say, well, I is something we invented to deal with solutions that, aren't real numbers. And I say, huh? So I say, look, you said that no real number squared could be negative, right? X squared can't equal negative. And so we said, that so we're going to define this number I is going to be the number that when you square it, you get a negative. You might say, well, we don't have a number that does. And I say, I know. That's what we're making. We are making the number that when squared is negative. And in particular, I squared, we're going to define to be negative 1. Meaning, I is the number that when multiplied with itself gets you negative 1. Yeah? And so we can represent I itself as the square root of negative 1. Yeah? That is basically, it's a square root of a negative, which you would say, you can't take the negative square root of it, and I know, but that's what that's why we're inventing this. We're creating this to deal with the fact that real numbers can't be square rooted if they're negative. And so we're making up, so they call them imaginary numbers. I, being the square root of negative 1, is called the imaginary unit. And we say unit, unit. Unit is like the counting value. So the unit in the real numbers is 1 because our counting numbers are by 1. 1, 2, 3, 4, 5, right? They're all 1 apart. I is the imaginary unit. So each imaginary is I apart. So it's I, 2I, 3I, 4I, 5I, so forth, right? So I is the unit of counting for imaginary numbers. And what we're going to do today in this lesson is sort of explore how you do operations with imaginary numbers, maybe some interesting properties about them, things like that, okay? Something to note about complex numbers is that they behave just like real numbers. There's a lot of, all the stuff we can do with real numbers, you can pretty much do with complex. There's some differences here and there, but by and large, they behave mostly the same. And this is very helpful. It's interesting, but also helpful. And so we're going to get to operation in a second here, but a little bit of math history here. Because you might be saying, Mr. Spake, this might be your face right now. And you'd say, imaginary. You say, imagine. You say, we're just making stuff up now? And I would say, yes, we are. We are, actually. But here's some history, because maybe you have a complaint about this word imaginary. I'll say, well, you wouldn't be the first one, because where does this term come from? I said, well, the 17th century French mathematician, René Descartes. This is, I think, therefore, I am. Yeah? That's this guy. You probably heard that quote before. French philosopher, big into political science, philosophy, but also just philosophy about life, but also a prominent mathematician of the time. You can actually thank him a lot for the stuff and notation we do in algebra. So around this time period, we're encountering the square root of negatives, so we're putting them under investigation. We're kind of considering them and things like that. But René Descartes sees the square root of a negative, and he says, this is stupid. This is dumb. Descartes says, what? You can't take the square root of a negative. This is fictitious. It is useless. Why would I do this? Because you can't represent this quantity, physically, right? And you'd say, well, but can you really do negative numbers physically, right? So, if you believe in negative numbers, why wouldn't you believe in this? Why can't you take the square root of a negative? Descartes is the one who started calling them imaginary numbers. And this was an insult, yeah? He didn't like the idea. He thought this was dumb, and so he called it made up. He said, hey, these are just fake numbers, because this is just, imagined. Someone is just playing around and imagining things, and it's not serious and not worthy of studying, right? Interestingly enough, this term has stuck with us. So, unlike Descartes back then, there's many uses for imaginary numbers today. And we can thank some of the work from Leonard Euler, Cauchy, and your favorite, someone we talked about in Unit 3, Gauss. Yeah, Gauss, one of the biggest names in math there is. Euler is a huge name too, but so is Cauchy. These three guys, and it's not just them three, there's plenty of other people too, but these three guys do a bunch of investigation with imaginary numbers, and then they basically create an entirely new field of math around the study of complexes. So they're like, actually, you know what? I'm going to look at these square root of negatives and really look at how they behave and interact with other numbers, right? And other functions and relationships and stuff like that. They do all this, and they come up with something called, I shouldn't say they came up, they don't call it complex analysis, but that is the topic you can study in college, yeah? Complex analysis is the study of complex numbers and their interaction and things like that. And as it turns out, they're very useful. Descartes, back in the 1600s, he's dismissing these as stupid, fictitious, useless, imagined, right? Imaginary numbers. And it isn't until 200 years later that people say, hold on. Wait a minute, buy into this. Look at this. Look how powerful this tool is. And you might be saying, well, okay, thank you, Mr. Spake. You're telling me it's powerful, but why? And I say, well, go talk to an electrical engineer. If you want to be convinced about how these can be useful, I think they may have an argument for you. Yeah, because if you study electrical engineering, look, Mr. Spake is not an electrical engineer, although I guess that's false. Mr. Spake is an electrical engineer, but it's Mr. Spake Sr. It's my dad. My dad is an electrical engineer. I am more of a mathematician, math teacher, math educator, right? But, you could talk to someone and they'll tell you about how when you're dealing with voltage and circuits, resistors and stuff like that, I is actually an extremely powerful tool in analyzing those circuits and all that, right? You might say, why is that? Well, there's a really cool relationship between the sine function, cosine function, and I. I'm not going to get into that right now. It's something you could Google if you like. But sine and cosine are sort of cyclical functions. They sort of repeat upon themselves. I does the similar thing. And so there's a really interesting relationship between the two. And so you can make, essentially what it does is you can make really, really hard problems very, very easy. Yeah, that is the power of complex numbers. You can take something extremely difficult or maybe not extremely, but tedious or tiresome or whatever. You can replace it with I, and then boop, you're done. You might say, okay, great. Why do I care about that? And I say, well, don't you enjoy the fact that when you press play on a video, it plays instantly, right? And everything streams and everything's instant, right? I can, ooh, look, my pen, it's instant, right? Everything is happening at an instant, right? Imaginary numbers kind of play a role in this sort of instantaneous, our ability to compute things fast, for things to process fast. Imaginary numbers play a role in that, yeah? But I'm not gonna. That's enough about that. Let's go ahead and get into operations with complex numbers. And all of this was just preliminary, understanding what they are, kind of where they come from, stuff like that, right? Some history. Let's look at some operations. Let's actually do some math with these. And this is actually pretty quick. The majority of this video was me just talking about all that stuff. So simplifying a complex expression. So as I mentioned, complex numbers are written of the form a plus bi. This means they can always be written this way, where a is called the real component, right? And then this is the imaginary component. Right? Now, what's great about a plus bi is say, well, look, 2 plus 3i, those aren't like terms. Real is different from imaginary, so this doesn't combine to make 5i. It just stays 2 plus 3i. So if I look at example 1 here, it says 2 plus 10i minus 4 minus 2i. I say, well, look, basic distribution property still holds. So 2 plus 10i minus 4, and then negative makes plus 2i. And you just group like terms, and you say, well, what are the real numbers? The real numbers are 2 and negative 4. So 2 minus 4 is negative 2. And then you say, well, what are the imaginary numbers? And I'd say, well, the imaginary numbers are 10i and 2i. So 10i plus 2i is 12i. And then we are done, right? So adding complex numbers is easy. It's literally just combining like terms, right? Pair the reals with the reals and the imaginaries with the imaginaries. Combine like terms, you're done, okay? Let's look at multiplication. This is where it gets a little more interesting because it's not just combining like terms. It's thinking deeper about it. So we'll do a basic binomial distribution, right? We'll say 4 distributes to 2, so 4 times 2 is 8. And then 4 distributes to negative 6i, so that's negative 24i. And then I times 2 is 2i. And then I times negative 6i is negative 6i squared, right? And you'll notice these two i's in the middle. We can clean that up real quick. Negative 24i plus 2i are like terms, making negative 22i. But you'll notice that we have this negative 6i squared business. You say, I just said that any complex number can be written of the form a plus bi. Yeah? Notice that there's no I squared in there, meaning we can sort of simplify this so we can get rid of it. I said, well, I was called the square root of negative 1, and we actually got this because we define I to be the number that when squared is -1, right? So I squared is -1. It's by definition, by virtue of our definition, I squared is called -1. It is the number when squared is -1, right? As I so this is 8 minus 22i minus 6, and then I squared is just replaced with a -1. And this is notable because you say, well, look, I itself is imaginary, but I squared, well, -1 is a real number. This is interesting. So then 8 and then -6 times -1, well, -6 times, that's +6. So 8 plus 6 is 14. And so you have your complex number. See how it's of the form a plus bi, right? Real plus imaginary, right? All of our numbers can be written that way. And actually, this would be a good moment for me to go back to the previous pages and actually mention this image down here just real quick. You'll notice that this entire box is complex numbers. And so what this means is real numbers are complex numbers. Everything is complex numbers. What's different is real from imaginary, because you see complex is the real and the imaginary component. So imaginary is just this idea of, I say, well, there's my imaginary number there, right? 2 plus root -1. But complex numbers are everything, okay? So yeah, they're kind of like the same thing, but like imaginary is different from real, okay? So there it is. Okay, example 3. It says f of x is this quadratic. So, okay, we're dipping our toe back into quadratics, right? Let's look at this. I've got x squared minus 4x plus 7. The goal says to evaluate f at a complex domain value, 2 plus I. We don't usually do that. And then determine whether the result is real or complex. So, as a reminder, because some of us need this, what does it mean to evaluate a function? So like if f of x is blah, 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 blah. What's f of 3? I said, well, f of 3 means to substitute x with 3. So every x that's in the equation becomes a 3. So it's 3 squared minus 4 times 3 plus 7, right? So when you say f of 2 plus I, that means to substitute x with 2 plus I. So then I say it's 2 plus I squared, like this, minus 4 times 2 plus I, and then a plus 7, okay? And all we're going to do is say, well, if the number is going to be complex, so it's got to be written as a plus bi, so we're just going to expand this and combine like terms. So 2 plus I squared, that's 2 plus I times itself, like so, minus 4 times 2 plus I plus 7. And, if you want to take a moment, maybe you would like to draw the box for your distributions, but I'm just going to go ahead and multiply. 2 times 2 is 4, and then a 2i, and then another 2i, plus 2i, and then an I times I, which is I squared, and then I'll distribute the -4, that's -8, minus 4i plus 7. So I'm just doing all my basic distributions there. And I might notice a few things. First of all, 2i plus 2i is 4i. In fact, it's positive 4i. And that's negative 4i right there. So those cancel each other out, pair out to 0, right? Also, I see an I squared here. And as we just discussed, I squared is defined to be -1. So if I replace I squared with -1, then basically what I have is 4 minus 1, and then a minus 8, and then a plus 7. And so let's just add those. 4 minus 1 is 3. 3 minus 8 is -5. -5 plus 7 is 2. And that's it. That's my answer, right? And this is a little interesting because if you think about it, x comma y, input comma, output. I said, well, you input a complex or imaginary expression, but you got out a real number. Because, right, it's just 2. It's just a number 2. So putting in something that sort of doesn't exist, spit out something that does? This is interesting, right? And also gives insight as to the use of complex numbers, right? Maybe that itself, you can't visualize it, he says whatever, but its output is real, which means you could see it somehow, right? It means it might be useful somehow, yeah? So yeah, that's my result. It's real. I'd encourage you, if you haven't done this lesson, if this is the first time you're watching it, I would pause the video and try this one for yourself right now. It's basically the thing we just did, evaluating f of negative 1 plus 3i. But especially if you're treating this like a real lesson, go ahead and do that. And then answer, what is significant about that result that you got? Yeah? Really think about it. What is significant about whatever answer you end up getting? And then, I'll talk about it. So here's the solution to this. Make sure we've got it. It's the same thing, plugging in negative 1 plus 3i. And this is negative 1 plus 3i quantity squared plus 2 times negative 1 plus 3i plus 10, right? Okay, I'm going to do all the same stuff. Da-da-da-da-da. I'm just going through the mechanics of algebra, right? I'm just saying, hey, what does it mean to square a number, right? This just means to multiply it by itself. And then I'll just do my distribution. Negative 1 times negative 1 is 1, and then a minus 3i, and then another minus 3i, and then 3 times 3 is 9, and I times I is I squared, and then that's 2 times negative 1, and then 2 times 3i, and then plus 10, right? I say, hey, notice something again. These two, so those make 6i. In fact, they make negative 6i. That's positive 6i. So, boop, those cancel each other. And again, that's 9i squared. I squared is negative 1. So that's 9 times negative 1, which is negative 9. And so if I make that simple substitution, I get 1 minus 9 minus 2 plus 10. Okay, well, negative 9 minus 2 is negative 11. And then 1 plus 10 is 11. So, boop, boop. 11 paired with negative 11 cancels. The result comes out to 0. This is interesting. And I ask you, what is interesting about this? I'm going to real time think about it, and I'm going to take a sip of water because I'm parched. It's refreshing. I'm ready. I'm ready to do the rest. Okay. Are you ready? I say, maybe you need a sip of water, right? Go ahead. Take a break if you need it. Okay. So what's significant about this result, right? Well, you plugged in something and it came out to 0. And of course, you might be saying, okay, well, 0. I guess 0 is a real number, so it's a real number again? I say, sure. I say, well, we learned about something in lesson 4.1. An important definition. And that definition was R is called a root if f of R is 0. I say, what? I say, so we talked about this definition. I said, this is something important. R is a root if f of R equals 0. Notice, we evaluated f of negative 1 plus 3i, and it came out to 0. This means f of negative 1 plus 3i equals 0. So what conclusion can you make? You say, therefore, this complex number, negative 1 plus 3i, is a root. It's a root. Yes. You say, Mr. Spake, who cares? I say, because this is interesting. I say, what is a root again? I mean, see, okay, it's what makes a function equal to 0. But graphically, right? What does it look graphically like? And I said, well, I'm going to erase some of this just for some sketching space. You don't have to draw this, but I want you to look at that again. X squared plus 2x plus 10. If you've covered lesson 4.2, then you know how to complete the square, right? And I say, okay, well, let's complete the square on this. Ax squared plus bx plus c. And you say, let's take the big guy, divide him by 2, then square it. And I say, well, so what's the b value? It's 2 times x. B is 2. So 2 to over 2 is 1. Squared is 1. So the magic number you add here is x squared plus 2x. And I'm going to say add 1. Then you're plus 10 minus 1. Minus 1 to keep it balanced. Group this trinomial and factor, right? What times itself is this polynomial? And you should get x plus 1 quantity squared. And of course, 10 minus 1 is plus 9. Hey, if you didn't follow along with that, you're like, what the heck is this guy doing? Go watch lesson 4.2 on completing the square. What I'm basically showing everyone right now is given standard form, you can write it in vertex form. And vertex form is cool because it tells you transformations, right? And transformations is cool because that gives you a sketch. And sketching a function quickly is a pretty useful tool, especially for calculus. So I'm going to put a little grid here, and I want you to sketch the function. X plus 1 squared, that's left 1, plus 9 up 9. So it looks like about right here is your vertex. And it's not stretched, and it's not flipped upside down, so it's probably going to look something like this-ish, right? Something more or less like that parabola right there, yeah? Now I want you to think about this. What was a root again? A root? So the synonyms you've learned in Algebra 1 about these, and also in 4.1, was you call them roots, you call them zeros, you call them solutions, and graphically you call them x-intercepts. But notice, does this parabola touch the x-axis? And I would say no, it doesn't. This parabola doesn't touch the x-axis, so you would say it has no real roots. So notice, and maybe we mentioned this in the last video, I don't know, but you wouldn't say it has no roots because actually it does. -1 plus 3i is a root because when you plug it in, it equals 0. But you can't visualize it here because this is a real axis, right? This x-axis is real numbers. And our solution doesn't lie on that number line. It lies somewhere else, yeah? Just a little heads up with roots versus x-intercepts, right? X-intercepts are roots. This is true, but you might not see a root on the x-axis, right? It might be, quote-unquote, imaginary, yeah? Neat. This is interesting. Okay, a few more things, and then I think I'll actually end the video so I can separate the other half. Okay. The next up is powers of I. So following, just seeing how I behaves. And this part is why, as I said, electrical engineering, right? Electrical engineers, they might tell you, hey, it's this part that really helps connect the usefulness of I to programming, to working with circuits and computer systems and all that good stuff, yeah? Again, I'm not an electrical engineer, but you could go ask one and they'd probably know. I suppose you could ask my dad if you want to hit him up, I guess. So powers of I. Calculate the following. I said, well, we know the first two. I is, of course, itself I. Right? I is I. Well, I don't disagree. I squared, we said, well, that's the square root of -1 squared, and we actually define I squared to be -1. So those two are kind of given, right? We just know this because we're the ones that made it up. So, but now let's take a deeper look at the powers of I. What does it mean to do I cubed? That means to do, say, I cubed means I times I times I, right? It's 3 i's multiplied together. Well, the thing is, on the previous one, we actually just saw that I squared was -1. So that's I times I times I times, right? So that's 2 i's, which makes a -1 times an I. Well, so then that means it's -1 times I means it's just -I. Neat. Okay. Let's look at I to the 4th. So here's I to the 4th. This equals I times I times I times I. And I say, okay, well, we just said that 2 i's makes -1, so these 2 i's also make -1, but these are in multiplication with each other. That's -1 times -1, and that becomes out to 1, positive 1. So I to the 4th is 1. Neat. I like this. So then, okay, let's look at I to the 5th. That's I times I times I times I times I. That's 5 of them. But we just talked about 4. 4 i's multiplied are equal to 1. So then this is just 1 times I. Well, then I to the 5th is just I. Ooh. Look at that. We're right there. We're sort of right back where we started. So then what is I to the 6th? And I say, well, I to the 6th means I times I, right? And say, so that's all of those. That's 4 i's, which makes 1, and 2 i's, which makes -1. So it's 1 times -1 is -1. Ooh, hey, that's -1. Are you starting to notice a pattern? Think I to the 7th. I to the 7th. That's 1, 2, 3, 4 i's, and then 1, 2, 3 more i's. These 4 i's make 1, and these 3 i's, as evidenced right here, say I cubed is just -I, so it's 1 times -I makes this -I. And so hopefully you're starting to see a pattern here, especially with the way I organize this. Can you predict what I to the 8th is going to be? And I would say, yes, you pattern recognizing, amazing Homo sapien. I to the 8th is 1, right? I to the 9th would be I. I to the 10th would be -1. I to the 11th would be -I. And I to the 12th would be 1. And so you can see the sort of cycles, right? It's I is cyclic. It's repeat. It's going every 4 powers. It repeats on itself again, right? And so it says, what pattern do you notice? Well, I just said it, right? Every 4 powers, 1, 2, 3, 4. Then it goes back and repeats. Between these 4 values, basically, right? It's kind of interesting. I say, what other numbers even do that, right? What other numbers, when you raise them to powers, cycle through themselves this way? That's kind of interesting, right? Now, let's look at some higher powers of I. So, like, here's I to the 25th. So how would you do this? I said, well, I to the 25th power. That sure is a lot of i's. And I said, well, you see how these are all 1s? So I to the 4th, I to the 8th, I to the 12th, I to the 16th, I to the 20th, I to the 24th. And you know what? These would be 1, 1, 1. But then 25 would just come after that, right? 25 would just be the one after 24. So 24 would be 1, meaning 25 would just be I. Hey, look at that. And you're done. So you just know what I to the 25th is. What would I to the 2019 be? Say, I to the 2019. I said, well, how could you do this? Well, Well, you're not gonna you're not gonna come out amount 2,000 times. That would be just exhausting. But you could say this, right? Every 4 powers, it ends at a 1. And that's kind of nice, right? Because if I land on a 4, I'm a 1. And even if I'm not a 4, if I just kind of go 1, 2, 3 after it, I could kind of find, which of those 3 I'm going to be. So here's an idea. Here's the power 2019. Let's go ahead and divide that by 4. 2019 divided by 4. So 4 goes into 25 times. And then it goes into 1 0 times. So then it goes into 19 4 times. You get 30 here. 4 goes into 30. Well, I don't need to do the whole decimal. I don't need to do that. It's just 3, right? You have 3 left over. I don't know. I was just used to doing decimals. So you have a remainder 3. And I say, well, so what does that mean? It means you went 1, 2, 3, 4, 1, 5, 1, 8, 9, 10, 11, 12. And you went through that cycle 504 times, right? And then eventually you're there and it says remainder 3. So, on the 504th round, you're right here. And then remainder 3 means you just go 1, 2, 3. So the remainder is actually going to tell you that, it ended at I cubed, meaning it's negative I. Yeah? So essentially that remainder tells you which of the 4 sort of core pattern you're going to land on, right? You might be saying, I'm not sure I follow. And can you give me a better, stronger, maybe proof of this? It's not really a proof, but just like an argument as to why that works. So we saw that it goes in 504 times. So that means, look, 504 times 4, that's 16, 0, 1. Okay, so that's 2016, right? So that means you can say, here's I to the 2016 plus 3. And actually a property of exponents is that if you have this addition, you can separate this like this. I to the 2016 times I to the 3. And because 2016 is divisible by 4, you know that I to the 2016 is 1. So it's 1 times I cubed, and we know that I cubed is negative I, right? And so you're done. And even if you don't buy that, even if you say, I don't really buy that I to the 2016 is 1, I say, well, based off that division, right, you do know that I to the 4th to the 504th power is 2016, right? And so that's 1 to the 504th power, which is just 1 times I cubed, right? You don't really have to worry about that. The strategy is, as it says down here, the strategy you can use to calculate I to some really high power is just divide the exponent by 4 and look at the remainder, right? And that's pretty much it. You divide it by 4, look at the remainder. Whatever the remainder is, it's going to correspond with these exponents. If it's remainder 1, it will be I. If it's remainder 2, it will be negative 1. And if it's remainder 3, it'll be negative I. And of course, if there's no remainder, then it was I to the 4th because it divided evenly into it. And thus we are done. Yes. Okay. Okay. All right. So that covers most of what we're talking about with complex numbers for this lesson, but we're not done yet. The next piece is on simplifying radicals. And so we're going to keep on going with this lesson and keep talking about these, and maybe I'll try to make the next one not so long because I was kind of yapping on this one, wasn't I, guys? I was kind of yapping. I said yap, yap, Yeah, Mr. Spake. He just doesn't shut up. I say, I'm going to do this in the next video. I'm going to separate these so we can talk about simplifying radicals, which is a review from Algebra 1. And then there is some more important stuff on rationalizing the denominators, which sort of connects with rationals, but also comes back to complex numbers. And so I'm going to talk about that in part 2. Okay, so that'll end this video. But go straight into part 2 because you need to see both of these for the full lesson. Anyway, take care. See you in the next one.